We have three principles, can say, in elastic analysis. One is called equilibrium and compatibility and stress strain relation. So we make use of these three principles to solve any problems in the elastic analysis. Usually, if your problems are statically determinate, I can find out all the forces, all the reactions, everything I can find out from the equilibrium equation, and then we will be using force displacement relation to get the displacement, and that is what your stress strain relation. And if your problem is statically indeterminate, then we have to use your compatibility equation. So basically, we have three principles: equilibrium, compatibility, and stress strain relation to solve any problems in the elastic analysis. Similarly, we have three principles, we can say, or three conditions for your plastic analysis, and one is called mechanism condition, and equilibrium condition, and yield condition. And equilibrium condition is common in both in elastic as well as plastic analysis. So whatever is your analysis, equilibrium is that is a mandatory condition. It has to satisfy the equilibrium. Equilibrium means at any stage your structure must be all the forces and moment. The algebraic sum it should be zero. Okay. And the mechanical condition means, and at failure stage, your the structure must form a mechanism. Okay, that is what the mechanism condition is meaning. And another one is yield condition that indicates the bending moment at any section. It should not exceed your plastic moment capacity. That is the maximum moment the cross section can resist. Okay, that is the limiting condition. That is the three basic principles which we'll be using in your plastic analysis. So this already we have discussed. Plastic yield condition, which means your moment at any section should not exceed your empty value. Okay, and equilibrium condition and the mechanism condition. Okay, the mechanism condition, that essentially that meaning is at failure your structure must form a mechanism. Then only the failure should happen. Okay, and to form the mechanism, we have discussed already, there should be enough number of plastic hinges that is equal to r plus 1. Okay, and where r is a r is your degree of static indeterminacy of your structure. Okay, and that is actually when we are considering your structure as a whole. Okay, that case, to form the mechanism, there should be r plus 1 number of plastic hinges. So mechanism, the meaning of mechanism is that is a state of structure. It cannot resist any further loading. So that indicates the failure condition. As we discussed, there are three conditions in the plastic analysis: equilibrium, mechanism, and yield condition. But many times or sometimes we can say all the three conditions may not satisfy. Okay, and if we are if you are doing a plastic analysis, or if your solution is satisfying only mechanism and equilibrium condition, then that solution will be calling upper bound solution. Okay, and that means and similarly, if your solution is satisfying only equilibrium condition and the yield condition, that solution is known as lower bound solution. Okay, and the equilibrium condition anyway it has to satisfy. That is common. It is in all the type of analysis and all type of solution. Your equilibrium condition is compulsory. It has to satisfy equilibrium anyway. Okay, and apart from equilibrium, any other one condition, either mechanism or yield condition. So depends upon that we have two types of solution: upper bound and lower bound solution, or we have two theorems. You can say upper bound theorem and lower bound theorem. And in lower bound solution, the yield condition and equilibrium condition is satisfied, but mechanism has not yet formed. Okay, that means finally your structure will collapse after forming the mechanism. Okay, and that means your yield condition, equilibrium condition is satisfied, but there is no mechanism is not yet formed. Okay, and that means your structure can take some more load. It is having some more capacity left in the structural members. That is why in the lower bound solution you will get a solution. Okay, and you will get a solution. That means you will get the value of collapse load that will be lower than the actual collapse load. Okay, that is what I have written. We will get a solution in the lower bound. So in this case, we will get a solution, and which is lower than it should be. Okay, which is actually it is lower than the actual solution or actual value for collapse load. So we will get a solution in the lower bound theorem. We will get a value for the collapse load which will be less than or equal to your actual collapse. Okay, and similarly in the upper bound solution, the mechanism is already formed and the equilibrium condition anyway it was satisfied, but the yield condition is not satisfied. That means your cross section, the the bending moment has not yet reached the plastic moment. Okay, so in that case, you will get the value for the collapse load, and that will be more than your actual solution. Okay, so maybe I can give you a so it will be something like this. Suppose this is my actual solution. This is my collapse load. Let us say actual solution. Okay. So in the lower bound theorem or lower bound solution, that means you will get the value of collapse load. Maybe that will be less than or equal to your actual solution. You will get in this region. Okay, that is your lower bound solution. It can be equal to collapse load many times, and it can be less than or equal to collapse load also. Okay, and similarly, in your upper bound solution will be coming in the other side. It will be more than your actual collapse load. So it can be equal to collapse load or it can be more than. So that is your upper bound solution. So actually this upper bound solution that indicates your upper limit for your collapse load. That actually we are getting the solution in this range. Okay, and the upper bound solution indicates the upper limit for your collapse load, and the lower bound solution indicates your lower limit. Okay, and when these two all the three conditions, because the upper bound solution had satisfying only two conditions, mechanism and equilibrium. That is why there can be variation from the actual solution. Okay, and the lower bound solution satisfying only yield and equilibrium conditions, so that there can be a variation in this range. So when all these three conditions are satisfied, mechanism, equilibrium and yield condition, then you will get your true solution. You will get your true solution. Okay, but many times for the simple problems you will find that your upper bound and lower bound solution will give you the same answer, but in some problems you will find that there will be variation. Upper bound solution will give you a slightly higher approximate value, and the lower bound solution may give you a different value. Okay, but this will be the range. Upper bound solution will be always, it will be more than, greater than or equal to the true solution, and the lower bound solution will be less than or equal to the true solution. So that is the meaning of upper bound and lower bound. So this we have already discussed moment curvature relation. Okay. Initially the curvature will be proportional to moment in the linear range. Then it will be in the rate of change of curvature will be at a faster rate, that is relaxed plastic range, and finally it will become the infinity. Infinity indicates with very less change of moment, it can have large curvature. So then we have discussed what is the condition to form mechanism. There should be ds plus 1, static indeterminacy plus 1 number of plastic hinges in the structure. That time it will convert your structure into a mechanism. Okay, that is the condition to form the mechanism. Then we have discussed different types of mechanism. One is called beam mechanism, then sway mechanism, then we can have a gable mechanism or joint mechanism, and we can also have a combined mechanism. Combined mechanism or composite mechanism, that means it is a combination of two independent mechanisms. So it can be combination of your beam and sway mechanism. All these are, you can say, these are independent mechanisms. So any two independent mechanisms you can combine to form a combined mechanism. So sometimes in the structure, the combined mechanism may be the governing failure. Okay. So that is why we have to look at all these types of mechanisms when you are solving for the collapse load for a given structure. And beam mechanism, that indicates we will be taking the individual span of your structure separate. Like if you have a continuous beam, 3-span continuous beam, there can be 3 beam mechanisms. Okay, and if you have a frame, one story frame like this, and we can take this column, and suppose if we have some load in the column, we can like this. So I can take this span separate, and we can check for the beam mechanism here also. Okay, beam mechanism does not mean that it's only for the beam. It is applicable for all the type of structures, continuous beams and frame as also. Only thing is we will take all the loaded span behave as a beam mechanism. We will take one by one span, then we can check for the beam mechanism. And sway mechanism is mainly due to the lateral load in the structure, and okay, and we have to see the combined mechanism also. Combined mechanism we have already discussed yesterday, so we will be seeing in the numerical example. And then we have seen how many number of independent mechanisms are possible. So that is that will give you a simple equation n minus r, where n is your number of possible plastic hinges and your r is your number of degree of static indeterminacy. that many number of independent mechanisms. So we have to check all the possible mechanisms finally. That is why we have to check this number always. We should not miss any mechanism. Okay, we have to check all the possible mechanisms, including the combined mechanism. Then only we can say that this is my collapse load for your structure. Okay. So then we have seen possible location for the plastic hinges. We have discussed already that it can be at the fixed end, it can be at the rigid joint of a frame, or it can be at the internal support of your continuous beam, or it can be wherever you have a change of cross section, and there a plastic hinge can form. And similarly, we have a change of material at that section also plastic hinge it can form, and wherever we have the maximum bending moment or zero shear push, that is also a possible location for the plastic hinge. So we have to check all these locations. So based on this only we are going to get your number of independent mechanisms. Okay, and after that we have discussed, I think. So if you have a structure, okay, if you have a frame or if you have a structure, if the number of plastic hinges are equal to the number of plastic hinges in the structure, that is equal to R plus 1. Okay, and here where R is your static indeterminate. So then we can say that your structure as a whole, it has collapsed. That indicates the total collapse of your structure. Okay, and in other ways, other case, like if the number of plastic hinges are less than R plus 1, where R is your degree of static indeterminacy, then we can say that a part of the structure has failed. But the structure as a whole, it has not failed. Only part of the structure has failed. For example, yesterday what we discussed the last slide. Suppose if you have a continuous beam and if you want to say the total structure has collapsed, then there should be 4 number of plastic hinges. But instead of that, I can take this span separate. Suppose the 3 hinges are formed in this span, then that indicates this span as there is a failure in the this span, but there is no failure in the remaining 2 span. Okay, that indicates your structure has failed, not complete collapse, but there is a partial failure in this. A part of a structure has failed. That we can call that is a partial collapse. The structure has failed partially. Okay. So this is called the partial collapse. There is no collapse as a structure as a whole. Okay, but that even that part of a structure is collapsed. Okay, that may make your structure is useless as a whole. Okay, even though you have a building frame and one story has failed. Oh, in the one story, all the beams and columns, so something like that, it has failed. All the beams have failed in the one story. So you cannot use that building. You have to repair that. That is what this condition is saying. If the number of plastic hinges are equal to R plus 1, where R is the degree of static indeterminacy of your structure as a whole, then you can say that your total collapse of your structure. Otherwise, only a part of a structure is getting failed, but still we will take that is a failure of your structure, because after that we cannot use that structure. That is why both we will consider as a failure. Okay, so we should not look only for R plus 1, even though there may be less number of plastic hinges, still the structure it may collapse. That is why we have to check all the mechanisms. We have to check not only the combined mechanism where we will be considering the structure as a whole. We have to look at the beam mechanism. We have to look at each span of each beam. We have to take separate. We have to check for the collapse condition. Then only we can say that what is the collapse load for that particular building frame. So this is already we have discussed. These conditions of plastic analysis, that is nothing but your basic principles. Equilibrium condition, that indicate your all the equilibrium equations must be satisfied. And mechanism condition, that indicate your structure at collapse must be capable of forming a mechanism due to the formation of plastic hinge. Okay, the structure must be able to capable of forming a mechanism. Okay, mechanism means the first suppose we are applying the load, we are keep on increase the load. Your moment somewhere we have peak moment, the moment will be keep on increasing, it will reach plastic moment, so it will be then a plastic hinge will be forming at that location, and then it will again will keep on increase the load. That location cannot take any more load, so Further loading it cannot take. It will just distribute to the other location of your structure, other joints of your structure. So eventually what will happen? Other joints also will be getting empty plastic moment. So there also plastic hedge will form. So like that it should be able to distribute the load. Finally there will be R plus 1 number of plastic hinges, then your mechanism will be formed. So that should happen in the structure, in the real case. Okay, then only we can say that your structure is efficient. It should be able to distribute the load, even though somewhere the first load, the moment is concentrating at some location. After that, it should be able to distribute to the other location. That is possible when you have a highly indeterminate structure. We have already provided a lot of extra members so that even though there are some failure in some of the members, it will be able to distribute to the other location. That is what your mechanical condition is saying. The structure must be capable of forming a mechanism before the failure. And third one is very yield condition. We have already discussed. If all the three conditions are satisfied, then you will get a unique value as your solution. You will get a single value for the collapse load. That will be the lowest collapse load, we can say, the lowest plastic limit load is obtained if all the three conditions are satisfied. Otherwise, there can be variation like this. There can be a variation in upper bound and lower bound solution will give you different answers sometimes. Okay. So yeah. So however, if the equilibrium condition and any of the above two, that we already discussed, that is equilibrium condition mechanism first case, and equilibrium condition is the yield condition in the second case. So in that case, you will get an approximate value above or below the true collapse load. That means in upper bound solution, you will get a approximate value which may be greater than or equal to collapse load, and in lower bound solution you will get a value for the collapse load that will be less than or equal to actual collapse load. Okay, and finally we have to compute this collapse load. That is our ultimate goal. Okay, we have to compute this collapse load. We have to estimate how much load it can take. Okay, that usually we are obtaining, we are going to find out by using the the energy principle. We can say the work consideration. What we will do is we will take the external work done by the external load. So that will be equal to the internal work done. So we are using that principle to find out the value of collapse load. So while using this work consideration, automatically you have satisfied your equilibrium condition. So it's the energy principle. Already the forces must be in equilibrium. The equilibrium condition already satisfied, and here we are using this work energy principle. And apart from that, we have to check this condition, the moment diagram at plastic state, that we have to draw, and we have to make sure that the bending moment at any section should not exceed your plastic moment. So like this is how we will be satisfying all the three conditions. So we will come back to this point after explaining the theorems. Then we will understand how to do this. Okay, we will be making use of these conditions in your lower bound and upper bound theorem. So we will come back to this slide later on. Okay, then I will explain it. So then we have theorems of plastic analysis. So in simple structures like we have a simple span beam, simply supported beam, or cantilever beam, simple structures, there could be only one possible collapse mechanism. There may not be so many mechanisms. Okay, so hence that is not much difficult to solve it. We can easily solve it because there is only one mechanism we have to check, and correspondingly we can apply the work energy, we can apply the energy principle, and we can solve it. But in complex structures like frame or continuous beam, so there can be so many mechanisms. So we have to check, we have to investigate all possible mechanisms one by one. So we have to check all the beam mechanism. If there is any possibility of sway mechanism, we have to check that one also. And if there can be a combined mechanism, we have to check that one also. Then from all this mechanism and corresponding to each mechanism, I can find what is the corresponding collapse load. Okay, and the mechanism is indicating a collapse stage, a failure condition. So corresponding to that, what is the ultimate load the structure can take? So that I can estimate, and then the mechanism which gives the lowest load, that will be the governing one for your failure. That is why what we will do is we will take all the mechanisms. Let us say I have 5 mechanisms is possible in my my building frame. So I will be getting 5 different or same value for as a collapse load. So from that I will take the lowest value, and that will be the your failure load for your structure. Okay, and that failure mechanism. That mechanism will be the governing mode of failure. Your structure may fail in that way when you apply the load. Okay, so this process is actually guided by a set of theorems, and we have three theorems: lower bound, upper bound, and uniqueness theorem. And these theorems are actually based on those three conditions which we have discussed earlier: yield condition, and equilibrium condition, and mechanism condition. The lower bound theorem, which will be based on your yield condition and your equilibrium condition. Similarly, your upper bound may be based on your mechanism condition and your equilibrium condition. And uniqueness theorem is nothing but it is just a combined combination of lower bound, upper bound. So that we will discuss the upper bound and lower bound theorem. We will discuss how to do that. Okay. So first, let us discuss the statement of the theorem. So after that, we'll go into the numerical example. So then it will be simple. How to apply this theorem to the structures? That part is simple. But let us go through the what this theorem is saying. What is the statement? Let us discuss that. Okay. So this lower bound theorem. So maybe I will write LBT, lower bound theorem. It is also known as static theorem, or we can say safe theorem. Generally, it is known as lower bound theorem or static theorem. This terminology is not so common. Anyway, uh, it is known as static theorem or lower bound theorem or static method, you can say. Okay, so this method is lower bound theorem. This theorem statement is it is given like that: for a given frame and for a given structure and for a given frame and loading, if there exists any distribution of bending moment throughout the frame, okay, which is both safe and statically admissible with a set of load W, then the value of load W must be less than or equal to the collapse load. The statement is not very clear, but this is a statement I have taken directly uh, from some textbook. Okay, but the theorem, what is the meaning is simple. Okay, so so in this theorem, it is satisfying only equilibrium and yield condition. Okay, equilibrium and yield condition, and equilibrium condition means anyway it has to satisfy all the force and moment. It should be in equilibrium. That is what your equilibrium condition. That is anyway it has to satisfy. And yield condition, that meaning is what was yield condition? That means your bending moment at any section, it should be MB or it should be less than or equal to MB. It should not cross your MB. That is your limiting condition. Okay, and that is why while applying this theorem or in this theorem we will make use of the bending moment item. So we have a structure and we have some loading. It is possible that you can use this theorem if you are able to draw your moment diagram. Okay, that means for simple structures like single span, simply supported beam, fixed beam, we can use this. But when you come to complex structures, it is not possible to draw your moment diagram. So to get the moment diagram, that is a tedious job. So it is not applicable for that type of cases. Applicable, but it will be difficult. Okay. So in this theorem, it is satisfying the equilibrium yield condition, and yield condition is saying your moment at any section is equal to MB. So that is the critical state. So that condition it is satisfied. That is why we will make use of your bending moment diagram. So we will draw the moment diagram that I am calling the equilibrium bending moment diagram. That is a bending moment diagram at plastic state. We have to draw the bending moment diagram at the plastic state. From the moment diagram, I can estimate what is the corresponding collapse load. That is what this theorem is saying actually. But statement looks something not clear. So here some words are there. If there exists any distribution of bending moment throughout the frame, which is both safe. Okay, safe means this condition only. Okay, M is less than or equal to MB, and statically admissible. Okay, and this term admissible, that means that indicates equilibrium. That indicate your it should be in equilibrium. The structure should be in equilibrium. Okay, that is what this point is saying. Okay, the lower bound theorem satisfying equilibrium and yield condition. So that is why we will be make use of the bending moment diagram to solve to arrive the value collapse load by using the lower bound theorem. So this LBT, hence this lower bound theorem represent the lower limit to the true solution that we already discussed. because it is having only equilibrium and yield condition, the mechanism is not yet formed. Okay, that is why the structure can take some more load. Some capacity is left in your structural members. That is why this may be your true solution, but your lower bound solution or lower bound theorem will give you the values. It may be approximate, or it may be less than or equal to your collapse load. So your lower bound solution will be in this range. Okay, lower bound theorem will give you the solution. It will be less than or equal to your collapse load. That is what this point is saying. Okay, that we already discussed in the earlier. And since because it is estimating your collapse load, which will be less than your actual collapse load, that means this method will give you this method has maximum factor of safety. Okay, so actually this structure can take this much load, that is a true collapse load, but my solution is maybe equal to that, or maybe slightly less than that. That means I will be more safer side. So this method will give you higher factor of safety, and always it will give you a safe solution. Okay, maybe that is why this theorem, maybe also we can call it a safe theorem. How to apply this? I will explain this. Okay, after this, then it will be clear how to use it. Okay, the statement looks like this only. Maybe you don't need to remember the statement, but you have to understand these conditions only. So these are the lower bound solution means equilibrium and yield conditions are satisfied, and your solution may be less than or equal to collapse load. So we will make use of your bending moment diagram at the plastic state to solve it. That I will be explaining with the help of examples. Okay, and the next one is your upper bound solution. There is not much theory. Okay, only this much. And upper bound theorem, it is also known as kinematic or unsafe theorem. Kinematic theorem, generally it is known as kinematic theorem. And this theorem, the statement is like this. Again, I have taken from some textbook. For a given frame subjected to set of load W, the value of W which is found to correspond to any assumed mechanism must be either greater than or equal to the collapse load. Okay. So again, statement looks something not clear. So this theorem, as we have discussed, it is satisfying only out of three conditions. The upper bound theorem is based on equilibrium and mechanism condition. It is not your yield condition may not satisfy. Okay, that is why it will give you a value of your collapse load that will be just more than, greater than or equal to your collapse load. So as per this theorem, equilibrium condition is satisfied, and the mechanism also formed in the structure, but your yield condition may not satisfy. So mechanism is already formed. That means in this, while using this upper bound theorem, or in this method, to estimate your collapse load, we have to assume a mechanism. We have to assume a mechanism, and corresponding to the mechanism, we have to find out the collapse load. That is the procedure we have to do in this method. We will assume a mechanism, and your collapse load is found to correspond to any assumed mechanism. So upper bound theorem will give you a higher value. That means upper bound theorem represent upper limit for your true solution. Okay, upper limit for your true solution. Your true solution may be here. This is my true solution, but your upper bound solution may be greater than or equal to that. So this indicate this is your upper limit for your solution. Okay, and because we are actually my structure can take only this much amount of load, but your upper bound solution is giving it may be giving a higher value. That means you are going to a unsafe side. Okay, you are going to unsafe side as per this theorem. Okay, that is why this will give you less factor of safety compared to your lower bound solution. Okay, and also you can say it is a solution may be unsafe sometimes. Actually, this can take only this much amount of load, that is a collapse load, and but this solution is saying it can take more than that. But that is a wrong conclusion, I can say. So that is why it may give you unsafe result, or unsafe solution sometimes. That is why we can also call this one is unsafe theorem. Okay, and generally we will be calling upper bound theorem or kinematic theorem. So this is satisfying equilibrium and mechanism condition. So this while solving this, from when you come to solution part, it is simple how to apply that. So while using the lower bound solution, we will make use of your plastic bending moment diagram at the plastic state. And when you are solving by upper bound theorem, we will assume a mechanism, and corresponding to mechanism, we will solve the collapse load. And how to do this, we will see good number of example questions. We will explain. I will explain that. Okay, then it will be clear. So, and advantage I can say that the upper bound solution can be easily applied to wide range of problems. Okay, because the lower bound solution you have to draw the moment diagram, at least the shape you have to draw correctly, and you should be able to predict where will be the maximum moment. Then only you can apply. That is why your lower bound solution is applicable only for simple problems where you will be able to predict your bending moment diagram easily. Otherwise, you cannot apply that. So that is all about upper bound and lower bound theorem. And uniqueness theorem we won't discuss. It is nothing but it is the combined theorem. We will combine both static and kinematic theorem. It is not like a different. We will solve upper bound and lower bound theorem. We will combine the result and we will take the lowest value as your collapse. And that we are doing in the solution stage anyway. And so this will give you, if it combines both theorem, means it satisfying all the three conditions. So this will give you a true solution. The W is equal to W. So that is what you can say uniqueness theorem. It is simply combining the result from upper bound and lower bound, and maybe that we have to do in all the stuff. If your upper bound and lower bound solution is giving you a different value, then we have to check. You have to take that least value as your correct true solution, collapse load. That is what your uniqueness theorem is saying. Okay, so we will. That is all about the theory. So with this, I think we have completed almost all the theory, and the remaining thing, only remaining, what is remaining is only the problems. We have to just practice some example, typical problems we will be solving in the class. So I will give you the problem sheet. I will send you with some problems. So I will update that, and I will give you around 15 to 20 problems. So some problem we will be solving in the class, more than 10, and the remaining we can solve it. Similarly, we can solve other problems. Okay.
Sir, can you explain the statement of the lower bound theorem again?
I will clarify through this numerical example. That is fine.
Yes, sir.
Okay. So we discuss here. So we will go for the first question. We have to find collapse load. Okay, we have all the question we are doing. Find out collapse load for a given structure. So first we will take all the simple case, simple beam. Then we will go to continuous beam and frame. Okay, so the first, I think we have time, 20-minute time is there, so we can. Yeah. First, we have a simply supported beam. Find out collapse load. That is your question. Okay, find out. So all these questions we will use both upper bound and lower bound solution. The procedure I will be explaining. Okay, so you can follow the same procedure for other problems. Find out collapse load. So we will be solving simply supported beam, fixed beam, then prop cantilever, then we will go to the continuous beam. Okay, and then we will go to the frame. Find out collapse load using static and kinematic theorem, using upper bound and lower bound. First, let us apply the static method. The static method. So lower bound theorem. First, let us apply this method. So this method, so it is satisfying your yield condition and your equilibrium condition. So we have to draw the moment diagram at the plastic state. Then we can solve for the collapse load. Okay, that is what we will be doing in the lower bound theorem. So what is the bending moment diagram for this beam? So the moment diagram will be like this. You will have a triangular bending moment diagram. It will be like this. So if you just draw your moment diagram in the, let us say, in the elastic range, for we are applying very small amount of load. What is the moment diagram? So this will be like this: PL by 4 moment at the center, that is PL by 4. Let us say this is your bending moment diagram. At elastic state. Okay, as usual, right? So at the plastic state means we are keep on increase the load. We have to find the collapse load. Let us say PC. So this loading condition is given. It is not the load value. Loading condition is given. I have a simply supported beam and I am applying a some concentrated load at the center, at the midspan. And what is the collapse load of my structure? That means I am going to keep on increase the load, how much load it can take at the failure. Okay, that is what the question. First we are applying the static method or lower bound solution to solve that. So in this method we have to draw the moment diagram at the plastic state, because we have to go up to the, it is satisfying the lower bound solution, it is satisfying your equilibrium and yield condition. Okay, so this that means yield condition means your cross-sectional moment should be MP. That is happening at the ultimate stage. So you are keep on increase the load, and what will happen if you keep on increase the load? All this section, all this moment value will be keep on increasing. And this is a section, I can say this is a section, we have the maximum value peak moment, so that moment will reach the peak moment or plastic moment first. So that means while drawing the moment at the moment diagram at the plastic state, also simple, you draw the same thing only, there is no change. The bending moment diagram at plastic state, so this moment value will be, this will be your plastic moment. Okay, and also you can check in the beginning, I think you should check that it is a statically determinate structure, so degree of static indeterminacy will be 0, and number of hinges required, okay, number of, it is not required actually to but anyway we need this one for the upper bound theory anyway. The number of plastic hinges, that should be ds plus 1. So in this case only one plastic hinge is required to form for the collapse. So that means where the plastic hinge is going to form where at the center only. Plastic hinge is forming at this point only in this case. Because there is a point. This is the section we have the maximum moment. So this is your moment diagram. I would at plastic state, that is for MP. And what is this? What is this value actually? This value is nothing but PL by 4. It is at the plastic state, ultimate state. So you can replace your P with ultimate load, PUL by 4. Okay. So now it is simple. We can just equate MP equal to PU L by 4, and your collapse load PU, that will be equal to 4 times MB by L. That is the collapse load, and where MB is, what is your MB? That is the plastic moment capacity of the cross section. Okay, MB is nothing but sigma y into ZP. This is the plastic moment capacity, plastic capacity cross section, because the beam is given, it is having some dimension B and D, let us say square beam, rectangular beam, and if we know the B and D, it is having some plastic section modulus ZP BD square by 4, that value is fixed. Let us say this beam is made of steel, so it is having some yield strength sigma y, the strength of the material, so it is having the plastic moment capacity is fixed. MB is a constant value, MB is a fixed value for this beam cross section. So the 4 times MB by L, that is the collapse load for this beam. So that is what we are getting from the static method or lower bound theorem. Okay, this is how we have to draw your bending moment diagram at the plastic state. Then I can directly make use of the equation. Your MB, this is your MB, plastic moment, the peak value, that is equal to your PL by 4. So in this equation you have to just replace your P with ultimate load, because this is at the ultimate stage, at the plastic state. So this is how we have to solve it by using a static method. These are all simple examples, so it won't take any time. And also it is a simple method also. It is also very not difficult. And let me explain the kinematic method or upper bound solution. Kinematic or upper bound theorem. And here we are the equilibrium and mechanism. These two conditions will be satisfied. Okay, so that is why here we will make use. We have to assume mechanism, and we have to find the collapse load PU corresponding to the assumed mechanism. Okay, so for that we know the number of plastic hinges required to form the mechanism, that is 1. Okay, so number of plastic hinges for this is a determinate structure, so I need only one plastic hinges so to form a mechanism. So you can also check all those things, that is actually not needed here. So like how many possible plastic hinge locations are here? Only one. This is only possible plastic hinge location. Okay, and as per this slide, uh, we have a slide like this. So how many number of independent mechanism? How many mechanism will be there? That is n minus r. The possible plastic hinges n, capital N, that is equal to 1 in our case. Indeterminacy r is equal to 0. So n 1 minus 0. Only one mechanism is possible. Okay. You can just refer slide number 58 for that. So let me go to this. That part is not actually we don't need to check that. All the simple case only one mechanism will be there always. That is why I am not checking that. So number of mechanism possible. I am just giving you this thing we have to check when we are solving a large structure like continuous beam or frame. The number of mechanism that is equal to also 1. So we can refer slide number 58. Okay, so what is the mechanism? Here one hinge will be forming, that is your mechanism. So that will be like this. So this maybe I will draw here. This is my beam. I have a simply supported beam, and this is my loading. The plastic hinge will be forming at the center. So the mechanism will be like this. This is the plastic hinge, and the corresponding load will be your collapse load. So we are going to find out this collapse load corresponding to this assumed mechanism. Okay. So I can take, there will be once the mechanism has formed, this will be, it will be like a rigid bar. This will be just straight. Let us say this angle is theta. Because this load is at the center, this angle and this angle will be same, theta. And this length will be just L by 2. This will be L by 2. This is L by 2. And let us take this distance is delta. Okay, and this is your plastic hinge, and we have the plastic moment here. Okay. Okay, so this is our this is the, so we are discussing upper bound theorem. This is the mechanism. This is a possible mechanism in the simply supported wave which subjected to concentrated load at the center. So here we will use, it is a mechanism we have to we will solve by using the work condition or work conservation. We will take the external work done which is equal to internal work done. So the external work done means your load into the displacement. External. So we are applying the load is PC. That is the these are the mechanism. So this load will be PC, collapse load. So PC into delta. Okay, that is your external work done. And internal work done we will find like this. Internal work done. So this is the plastic hinge form. So here we have the moment is MB. Okay, and what will be this angle? This angle also will be theta. This is theta, and this is also theta. Okay, so usually we'll take the plastic hinge. This moment will be there. This is how we have to represent. MB will be there at the two sides. So the internal work done will be like force into displacement, or similarly you can find the uh, this is a yielded zone. So moment is MB, and we have the rotation theta. So the internal work done will be your plastic moment into theta. MB theta here and MB theta here. So it will be like this: MB into theta plus MB into theta. So you can write 2 times MP by theta. You can also write like this, why we are taking two sides. So only for this problem, I will explain that. Okay. So this is my mechanism, this first member, and this is second segment. Okay. What is the change in rotation between this? What is the rotation at this point? You will draw a tangent for the two members. This tangent for this member and tangent for this member. What is this angle? The total angle is 2 theta. Okay, and this here I have here MB. That way also you can write directly. Your internal work done will be MB into 2 times theta. Both ways, both are correct. So that is what we have to take the moment MB in the two both the side while assigning a hinge in the plastic hinge. So now as per this principle, the external work done and internal work done must be equal. And delta I can substitute in terms of theta, or I can say that theta is equal to delta by, because it is a straight line, and theta is equal to delta by small angle, like that we are all taking. Then theta is equal to delta by L by 2. That will become 2 times of delta by L. So I can substitute everything. This here 1, and this is your equation 2. So 1 is equal to 2. So PC into delta, that is equal to 2 MB into theta is equal to 2 delta by L. Okay, so this delta will be getting cancelled. This one can cancel, and PC is equal to 4 MB by L. Okay, so that is your solution from upper bound theorem, and the solution from the lower bound theorem also same. Okay, all the simple problems you will find that both this will give you the same value. There won't be any difference. Okay, so automatically the third condition is getting satisfied. So finally, now I can confirm also both the solution giving the same 4 MB by L. Now we can say that your true solution is also 4 MB by L only. And in case if it is different, you have to choose the minimum value among these. And now also I can say that if it is the case, if you keep on increasing load, how the structure is going to fail, your structure will fail like this. This will be the mechanism which will govern the failure of your beam. Finally, the plastic hinge will forming here, then the structure is going to fail. Okay, that is also we can confirm from, because this is a true solution. So this is a true solution anyway. There is no difference. Upper bound and lower bound theorem giving the same answer. So this is a true solution of the actual solution, actual value for the collapse load. So we can say that this is an actual mechanism. This is the mechanism which is governing your failure. Okay, this is the procedure you have to apply to solve the problem. So this is a simple example, symmetric load, and you can do this next one in the similar way. So this one you can do it as a homework. I don't want to explain that. So simple, you can draw the moment diagram. You will find that you can tell me the answer that you can draw. This will be the maximum moment PAB by L, which will be equal to MP. So you can get the value of this will be a collapse. PC will be equal to MBL by AAB. That is your lower bound theorem. You can solve it step by step like this. Draw the moment diagram at the plastic state, and then you can apply that. And if you are going for a upper bound theorem, the plastic hinge will form here. So it will become like this. This is your beam, and this is the plastic hinge, and like this. And here we'll have a theta 1, and here we'll have theta 2. Both the angle will be different. And this is my delta. Okay, and this is my PC. So here work done will be external will be PC times delta. What will be the internal work done? Internal work done will be, and this is my plastic hinge, and this is MB, this is theta 1, it is theta 2. So what will be the internal work done? That is MB into theta 1 plus MB into theta 2. So now we can write theta 1 is equal to delta by L, delta by A, it is a delta by A, that is theta 1, okay, and theta 2 is equal to delta by B. So you can substitute everything here and you can solve it, and you will get the same answer, PC equal to MB by L by AB.